All right, we've got this equation, y equals cos of x times sine x, and a sketch is given between 0 and pi. We're asked to find dy by dx. So we're going to use a product rule here. I'm going to let this one be u and this one be v. U prime, if I differentiate this, I can use the chain rule. Like I could write down all the steps of the chain rule, or I could just sort of do it in my head. So I'm going to differentiate cos of something, which is going to give me minus sine of that something. And then I just differentiate the inside with respect to x, which will give me minus sine x. So I'm left with sine of cos of x times sine x. Meanwhile, v dash is much more simple, cos x. So dy by dx is going to be u prime v. So I'm going to get a sine squared x there. So sine cos x, sine x times sine x, plus v prime u. So I'm going to get cos x v prime, times cos x. And that is going to be my answer. In part B, we are asked to verify that the turning point is at x equals pi over 2 and find the y coordinate of this point. So let me do this up here. Now what we don't want to do is try and set this equal to 0 and then solve it. Okay, they've just said to verify. So when x is equal to pi over 2, dy by dx. Now you can't just say equals 0, we need to give some indication of working. So it's going to be sine of cos pi over 2 sine pi over 2, which is, that is 0, plus cos of cos pi over 2, which is 0, but then it's cos of 0, times by cos pi over 2. So that's the crucial one. That one is 0. And hence this is equal to 0. This verifies it. The turning point is therefore at x equals pi over 2. We're asked to find y, so here y is equal to cos pi over 2 sine pi over 2. So that's going to be, this is 0, so it's going to be cos of 0, which is just 1, times by sine of pi over 2, which is 1. So we just get 1. And we're done. We're asked to find the area of the region between C1 and the positive x-axis between 0 and pi. That is going to be this region here. So we're going to need to integrate. Let's just leave that next bit for the moment. Now that's going to mean we need to integrate cos of cos x times sine x with respect to x. Now I think it's worth just leaving out the limits for the moment. Let's just focus on this. When I looked at this question, like a few things went through my mind. Okay, there's actually a really quick way of doing it, but I thought, hey, could we integrate by parts? But then you're going to have to because we have differentiated cos of cos x. But remember, that looked really complicated, not more simple. That's typically when you want to integrate by parts, when you got like x squared e to the x, and you can differentiate the x squared to make it a bit nicer, and then again. But here it's not actually going to become any nicer, and you don't want to be integrating this separately by itself either. So I thought, okay, I'll try try a little substitution. Let u equal cos x. That seems to make sense because I know the derivative is related to sine x, and I can then get a cos of u. So du by dx will equal minus sine x. And actually, remember, we want to change dx to dx by du. So what I want is dx by du, which is minus 1 over sine x. And this is great news because I can then write it as cos of u sine x times minus 1 over sine x du. These cancel, so I'm left with minus cos u du, which is going to be minus sine u plus c. Now I could have substituted the limits in. I'm not going to do that quite a second because actually what we get if we put back in for u is sine of cos x or minus sine of cos x plus c. And it kind of, yeah, that makes sense now, doesn't it? Because, basically how we could have done this question, it's easier to say it now, but we could use kind of it's not implicit, is it? It's sort of recognition, integration by recognition as such. So by noticing that when you differentiate sine of cos x, okay, this is going to change to a cos, and you're going to times by the derivative, which is minus sine, and that will work out. So if you don't see it, of course, this substitution works fine, but that is actually going to be better. And therefore, the integral from 0 to pi of cos x sine x with respect to x, that is going to equal minus sine cos x between 0 and pi. Now, cos of pi is actually minus 1. So I'm going to get minus sine minus 1. And then I'm going to minus sine cos 0 is just 1. So that is sine 1 minus sine to the minus 1. But we can simplify that further because actually minus sine x is identical to sine of minus x because it's an odd function. And therefore this is plus sine 1 and the final answer is 2 sine 1. Right, now we're into the main bit of the question, which is this thing here. We've got the same curve that we had before, C1, but now we've also got a sketch of y equals sine cos x sine x. And the first thing we're asked that, well, they intersect at the origin, as we can see, and when x is equal to pi. But there's another place where they intersect, and we're asked to find out those points, A and B in a form not including trig functions. Let's give it a go. So for this, I'm going to need to set that function. So so C1 and C2 intersect when cos of cos x sine x equals sine of cos x sine x. Now we get a solution straight away for this, and that is sine x equals 0. You can sort of divide through by it, but when you divide through by it, you have to remember that it could equal 0. Or cos x equals sine of cos x. Now, if we look at the first solution, you get 0 or pi. Those are the ones we already had. So it's going to be this one that gives us the solution that we're interested in here. Now, when I did this question, I thought, okay, I've got cos of something equals sine of something, and I know the point where cos and sine meet, and that is pi over 4. So cos x must equal pi over 4, because at both of those points, cos pi over 4 is 1 over root 2. If you don't spot that, then the mark scheme does it the following way. They actually, the more standard way to be fair, and it's to divide through by cos of cos x. So it'd actually be sine of cos x divided by cos of cos x, which is tan of cos x. And that would also, because tan of pi over 4 is 1, that would also lead to cos of x equaling pi over 4. So what that means is the a coordinate that we're interested in is going to be inverse cos of pi over 4. We can't leave it any more simply than that, and we weren't told that we couldn't leave a in terms of trig functions. We're gonna have to really. Now for b, I can substitute it back into either one, and I think it makes sense to put it back into here. So sub back in. B is going to equal cos of cos a, which is pi over 4, times sine of a, which is inverse cos pi over 4. So the first bit's fine, because that is just 1 over root 2. We've just got to sort out this bit. And you've got to remember the following, that cos squared plus sine squared is 1. So sine is going to be 1 minus cos squared square rooted. It looks awkward, but it will work. And therefore it's going to be 1 minus cos squared of inverse cos pi over 4. Now we find cos of inverse cos, which cancels, and then we're left with pi over 4, and then we square it. So we're going to get pi squared over 16. We're not asked to simplify it, but it's generally good practice to do that. And if you look at the next part, it's going to want us to find this area, which we're going to need to use it. So I think it does make sense. It is, like I said, good practice. Right, so let's get it basically common denominator of 16. So 16 minus pi squared all over 16. Or we can write it as 16 minus pi squared all divided by, now I can square root the 16 to give me 4, and I can write it as root 2 there. I just remembered actually, like we don't use that in the next part because it's the value of b, and we only use the value of a, which we've calculated as inverse cos pi over 4. So I didn't necessarily need to simplify it, but it does look a bit better now. It doesn't involve trig functions. That is our value for b. So we are left to find the shaded area. Actually, I just need to go right back to the start of the question to see it. Here we go. Find the area of the shaded region between C1 and C2. So I'm going to need to integrate from 0 to inverse cos pi over 4 under C2 to give this full area and then minus the integral of C1 between the same limits. Just got to get it the right way around. So the area is going to be the integral of sine cos x sine x between 0 and inverse cos pi over 4. And then I'm going to minus same limits cos x times sine x. Now we've actually already dealt with this one. Okay, so we're in a good place. So we just need to think about this one here. And this time I'm going to do it using inspection. I accidentally called it implicit integration. Nothing exists like that. It's inspection. So I can basically try cos of cos x and then think, oh, well, if I differentiate that, will I get this here? Well, when I differentiate, I will get, you can even sort of try it below. I'm going to get a minus sine of cos x, so that's good. And then I would times by the derivative of cos x, which is minus sine x. And yes, that will work. Brilliant. So I'm sorted actually. I'm going to put that one in the, yeah, I'm doing these separately. I could actually bring them under one integral if I wanted. And then we had very similar for the other one. Now I'm minusing, but for this one, if you recall, it was sine of cos x, but we had to stick a minus in front of it for it to work. But that's absolutely fine. So I am going to get cos of cos, um, sorry, cos of inverse cos pi over 4. That's just going to be cos of pi over 4. It's a bit confusing, isn't it? Minus cos of cos 0, which is 1. And then I can actually change this to a plus and then put this in a bracket. So it's going to be, it's going to be sine of pi over 4 minus sine of cos 0, which is 1. So not actually as bad as you might have first thought, because we're going to get 1 over root 2 minus cos 1 plus 1 over root 2 minus sine 1. 1 over root 2 plus 1 over root 2 is 2 over root 2, which is just root 2. So root 2 minus sine 1 minus cos 1. It's actually, if you can spot that to do inspection, it's pretty quick. Otherwise, you're going to need to do substitution. You might end up changing the limits. I understand why you might go along those lines, but yeah, this is a really solid method and pretty neat answer.